I'm delighted to introduce our speaker for today. He's really a very accomplished and sophisticated researcher in robotics. And I've known him for a while. He's joined the GRASP lab, so I got to meet him when he gave me a tour of the GRASP lab last year. And he also was a host of of ICRA, as you know. And he's actually going to become I think he's a program chair for RS.
No. I'm area chair.
Area chair?
Yeah.
All right.
It's not late for that.
All right. Well, he did his undergrad at Stanford, and then he went to MIT, and then he's been at Penn. He also did a stint at a company called Vecna, which is doing some humanoid robotics. And his research was really characterized by really this hybrid between classical control techniques and learning, which is, I think, is exactly what he's going to talk about today. I'm really excited to hear it. And he tries to basically develop very efficient algorithms and methods that operate on dynamical systems, and in applications from legged locomotion to grasping and manipulation. So when I saw his abstract today, I told all my students, you got to see this, it's going to be great. So please join me in welcoming Nick Foster.
Thanks a lot, and for having me and for that fantastic introduction. So throughout today, feel free to jump in with questions, right? You can certainly save things read, but if you want to turn this into a conversation at any point, you can argue with what I'm saying, by all means, jump in and we can digress. So I'm going to talk about some of the work we've been doing in my lab. All this is really coming out in the last 2 years or so, 2.5 years, thinking about, as the title implies, dexterity without big data. Okay, so, we've all probably seen these videos before, right? Nothing new here. We have a recent release from Boston Dynamics, and we have a nice video from OpenAI showing their work on solving this Rubik's Cube. And so, I think a question that comes to my mind, certainly one that's often in the mind of the public, is you see videos like this, right? It's just robots doing fantastic things, human-like capabilities, running, throwing stuff, jumping, dexterous manipulation. And so the question I think that we should be asking ourselves when we watch these videos is, when I look at my home, okay, when I probably look at your homes as well, why is this the robot I have? Okay, why do I have a Roomba and not something capable of really getting in and cleaning clothes and actually scrubbing things and putting together furniture, what have you? So so what's the difference here, right? And there's a lot of things we could point to, and there's a lot of things we could point to what enables OpenAI or enables Boston Dynamics. And I imagine you all are looking at this and you have your own little research agendas that point to specific parts of that problem. But I think one that we can probably agree on is that these problems were made somehow easier by the fact that engineers knew what problem they were solving. They had a lot of time to work in this particular environment in Waltham, Massachusetts, on getting the robot to throw stuff and so on. Right? Expertise went into that, carefully constructing those maneuvers. And the same thing I would say for OpenAI. They knew the problem they were solving. They were able to spend years of simulated time training a problem. And so when I look at kind of going from something like that to a task that I really care about, which is maybe more something like this, a robot's going to enter a room, whether that's your workplace or your kitchen or some other cluttered environment. It's going to encounter some stuff it's never seen before. And it's going to have to accomplish a task in that environment. It's going to have to do so in a modest amount of time. We're talking seconds to minutes, certainly not years of collecting data and training. So I'm very interested in this problem of achieving dynamic, dexterous behaviors in relatively unknown environments with minimal amounts of data. And again, there's lots of different parts of this problem we can pull apart, but I would say a key one here that we're interested in particular in my lab is how the robot is going to interact with the environment. So a key aspect of dealing with this clutter, of even running, jumping, throwing things, is that contact between robot and environment. And I would argue that's something that's sort of really critical here. And just to throw a couple of quotes out here, right? When OpenAI, right, eventually chose to move on from their robotics group, right? This was largely attributed to the lack of data for the types of algorithms they could achieve. Now they've gone on to do some other interesting things. Okay, maybe chatbots are somehow better than robots. or maybe they're just easier than robots, who knows, right? Well, that remains to be seen, but they sort of gave up on robotics because there wasn't enough data. And then again, to pull a quote here, okay, so this is from a review paper written by a number of folks here at Berkeley, among others, looking at reinforcement learning, and particularly sort of one of the observations that they came to was the fact that when robots touch the world, okay, so after a contact event, this is when whatever sort of predictive model you might have quickly diverges from reality. And there's this particular challenge interacting with the environment, and that's one that we really focused on. Okay, so within that context, I am today going to talk about some kind of model-based framework. Okay, you can choose to disagree with that if you like, but that's sort of the approach we're going to take here. And within this sort of broad paradigm of model-based control, I think roughly what most people do looks something like this. Okay, there's a lot of wiggle room in the details, but looks something like this. You have some kind of simple model planner, okay, that's producing some kind of output here. And that planner is maybe making longer horizon decisions at some kind of slower rate, produces some kind of task-based target, and then you have a lower level controller which is going to track that target using some kind of local model. And typically what this means is the first stage is some kind of contact planner maybe. So for a walking robot, maybe it's laying out footsteps. For manipulation, maybe it's deciding where and when to grasp an object. And then there's some kind of QP using local linearization. Maybe that QP is running, at 1,000 hertz or something like that for an NPC. Okay. So within this framework, I would say all of these pieces really kind of don't have answers right now when it comes to multimodality, when it comes to making and breaking contact. And so this talk, we're going to sort of poke at a few different aspects here. So we'll start by looking at the right side, looking at NPC in particular, and saying, well, I want to do NPC in a multi-contact domain that makes it break contact, that real time decides what to touch, where to touch, when to touch it. Well, this linearization is no good, and I'm going to need something else to deal with multimodality. And then we'll talk about where models come from. So I want to run a model-based controller. How do I learn a model from data and do so efficiently, particularly when that model involves touching stuff? And then the last part of the talk will focus more on the simple model concept, right? So if I want to deal with clutter, I cannot model the entire world. I'm going to have to make some sacrifices. And how do we make those sacrifices and what we model in an intelligent fashion? So that'll be the last part of the talk. So first, control. Okay, so this is the pure control aspect of the talk, and then we'll talk about it. Right, so linearization is no good, right? Right from the start, linearization effectively only can approximate one contact mode. No amount of local reasoning about waving my hands in the air is going to give me any kind of information about what it means to go out and touch a nearby surface. So linearization fundamentally is inappropriate for making decisions about how to interact with objects. And so the flip side of that, right, is that multi-contact inherently requires some degree of multimodality. Throughout a good chunk of this talk, we're going to work in this framework here of what's called a linear complementarity system. This is, the details are not super important unless you're interested, but this is a piecewise affine dynamical system. Each piece corresponds to a mode, and here we're enforcing these pieces via these complementarity constraints. So a common example here would be something like saying, my function phi is orthogonal to my contact force, and here phi is a signed distance. So this says distance can be 0, and then force can be non-zero. But if distance is non-zero, if I'm not touching, then the force has to be 0. It's an algebraic encoding with multimodality. The details, I'm happy to discuss maybe offline. But this is an approximation of multi-contact systems. I would say this nonlinear version, okay, is what's at the heart of all your favorite simulators. So all the simulators, Joko, Bullet, Gazebo, et cetera, Drake, and so on, are all looking at the nonlinear version of this, and they're trying to solve this nonlinear complementarity problem, and they're all making clever choices about how to do so in a tractable fashion. And even if you look at a simulator, so what makes a simulator special? How do they differentiate themselves from one another? It tends to be how they deal with approximated solutions to this problem. So we're going to take this nonlinear complementarity thing, and we're going to linearize the bits that can be linearized. This means we're going to linearize things like continuous forces. We're going to linearize things like geometry. All the functions which are differentiable, we're going to linearize, but we're going to leave multimodality. Because I think multimodality is really core to being able to make and break contact. And so we have this, at the end of the day, we have this piecewise affine system where the pieces correspond to those. Okay, so what does our NPC problem look like here? Well, in some sense, it looks a lot like our familiar NPC problems. Looks like a quadratic program, except we have these grids in blue, which represent non-convex quadratic constraints. So if you think about the forces, future states, future inputs, you end up with this non-convex quadratic constraint. That's an inequality constraint, which is difficult to deal with. There's lots of ways you could write this problem. So you could write this as a quadratically constrained QP, or you could equivalently convert it over to an MIQP. So we can see right off the bat, this is an NP hard problem. We're unlikely to solve this at real-time rates globally. Okay. So given that, right? Given that I think in robotics, it's pretty much a necessity, I would argue, to throw away global optimality from the beginning when looking at these NPC problems. We have to ask ourselves, what do we want from a suboptimal solution? And I say this because there's a lot of work actually in this area going on right now. Some fantastic work, for instance, from Zach Manchester's group and Carnegie Mellon, collaborating as well with folks at Stanford. So what do we want from suboptimality here? Like, what's important to us? I'd say there's a few things. So I think it's really important that this algorithm be able to explore multimodality. Right? If it simply restricts itself to whatever mode it's currently in, or whatever the nominal mode might be, or has very limited ability to explore beyond that, well, then it's kind of solving the traditional QP, but it's not going to be able to reach out and brace against something we're not calling. It's not going to be able to initiate contact to achieve some desired goal. It's important for these problems to get to a substantial prediction horizon. Okay? So things like very myopic single-step QPs or short horizon predictors aren't particularly useful in this setting, because if I want to see that this is beneficial, well, my prediction horizon sort of has to see all the way into the future where I'm going to reach out and make contact. And then lastly, it has to be fast. So these are the things we care about. I'll give one example of what we've done before I get into some of the details. This is a simulated version. Hardware results are coming a little bit later. So here we've given this robot, this Franka arm, the task of moving these balls forward. Okay. So the robot can touch either ball. The balls can touch one another. They can also touch the table. And real time, it's making decisions about how to interact with these objects. So at the beginning, when they're sort of more or less aligned, because that's the goal of getting them over to the left of the screen, it pushes the back one into the one in front, kind of sliding them along. Now, this is a particularly kind of unstable configuration. Eventually, they end up side by side. I skipped the middle part, which is less interesting. And once they're side by side, it's sort of going back and forth between pushing them. Coming up with this mode sequence automatically in real time. So what could we do here, right? What are some approaches? I would say in the context of history, this is actually a problem I've been thinking about since the second year of my PhD, right? So at the very beginning of my PhD, I did some work on trajectory optimization. Context, oh cool, I have a trajectory, let's track it, okay? 10 years later, a couple failed master's projects along the way. We actually have a solution. We've tried a bunch of stuff, not a bunch of stuff along the way. So just to sort of give an idea of what you might consider and why I think it's maybe not going to work, you might think of just saying, okay, let's solve this with big N, right? This is a mixed integer problem. You might as well try it with big N. You might also similarly say, well, I've heard of some really cool techniques to take these quadratic constraints and turn them into semi-definite constraints via some kind of convex relaxation. Both of these sort of suffer from the same problem. And so both of these work well when there are useful convex relaxations. And in this particular problem, the convex relaxation, anything I've seen is really useless at the end of the day. So if I take a convex relaxation of this constraint that says either I'm touching something or I have zero force, this multimodality problem, and you say, well, let's sort of fuzz that out and make a convex relaxation. It says, well, either I could be almost touching something or half touching something in the big M version with half force. And it turns out half touching something with half force is just a lot of force at a lot of distance. It's not a useful relaxation at the end of the day. So the lower bounds, for instance, you get from branch bound are particularly meaningless. And so these end up being very, very small. Orders of magnitude. You want to also try something like a differentiable contact model with some kind of gradient-based optimization. And this is, I think, probably the most popular approach right now. And this could work. I mean, there's some really nice results here that are just coming out now that are showing promise here. I think the challenge with this style of approach is this mode exploration bit, right? If you make your model really soft, it might get better at mode exploration, but then your model is less accurate. And how do you balance this trade-off, right? This trade-off between exploration and realism, and maybe you have to then go to some kind of homotopy approach for your change. It remains to be seen whether this will work for complex problems, but I think it's worth this point. But we did something a little bit different. You actually went to an ADMM based approach. And ADMM at its core works by splitting constraints. And in this case, the constraints kind of split very naturally. So our first stage is basically to throw out the hard part of the problem, the complementary constraints. We just solve a QP. And the second stage looks at that hard problem again. That's where the non-convexity lies. But the beauty of it here is that non-convexity is actually decoupled across time. So those complementary constraints, which are the hard bits, only really apply to the ith variables at a time. And so we get a bunch of independent subproblems. And again, this is sort of taken the hard aspect, the non-convexity, we can split it up into much smaller subproblems, and we can solve those subproblems via either a small scale MIQP or some kind of heuristic. So I'll show a few examples. This is a carpal we built in the lab. The carpal with some walls you can bang into. That's where the multimodality is coming from. Relatively few contact modes in this example. But we're showing, first off, that one will stabilize the system, and it has to reason about the contact to stabilize it. Linearization methods fail pretty quickly here. But also, for this example, we can actually go out and calculate the suboptimality of the approach. So we can do things like compare the approximate solution we get out of ADMM with the true MIQP solution, and we find this very little gap there. That's sort of the blue red lines. And in this case, even with a very crummy model, I would say, we actually treat these foam walls as springs, and we spent, about 10 minutes identifying the spring constants. A very crude model here for the system. It turns out that the predicted cost, loosely matches the real cost. More recently, this was work done over the summer. We haven't published this yet, but it's in prep. We put this on a Franka arm, and here we extract the arm as a single contact fork and finger, and give it the task of moving these balls around on the table. So moving them in different motions, whether it's circular motion or square or line. It can show that it responds well to perturbations. It's intelligently making decisions when to touch the ball, when to go and reset itself. We give a little bit of help here to deal with the fact that linear approximation of the geometry of the sphere is not particularly good. So we give it a little bit of help in terms of providing some idea that every once in a while it does have to probably reset itself. But more or less, it's making the hybrid decisions on its own.
Is there a fixed time or is it the full 3D?
This, so it depends on. You don't need to treat this as a full 3D problem. We treat the end effector in 3D because it does have to manage the height of the ball. For the multi-ball problems we're looking at, we have restricted the state dimension of the ball to be on the table, just from a complexity perspective. To be honest, on the one ball hardware examples, we hadn't done that software engineering yet, so it's doing a 3D model of the ball, even though it doesn't need to.
Yeah, for this example, what were the number? Like, do you have an idea of the number of non-convex regions or modes that you needed to solve?
So for the single ball example, we have contact between the ball and the table that can be sticking or sliding, and we have contact between the end effector and the ball that also can be sticking or sliding. So those are the ones that kind of drawn. For the two ball example, it's robot, ball, robot, other ball. So three possible contacts, and then exponential in that in terms of the number of possible combinations. And then over a prediction horizon, I think in this case, of 10 steps. So the MIQP version of that, right, was like 30 integer variables, 50 integer variables, something like that.
How do you have an estimate of how long those take to solve?
The MIQP.
Yeah.
I don't remember the exact number. I think some of it's in the paper, but it's at least an order of magnitude too slow. So we're solving this at around 50 hertz. So that's at least 10 times.
So what are the sensors of the end effector? We have a contact sensor or a force sensor?
No. Yeah, so this is pure impedance control on the end effector.
You probably need the contact sensor, right, for your...
I think so what we have not done here, and I think it's very much on the short-term horizon, is to do this, but in an adaptive setting, where we use force sensing to adjust our model online. So this is somewhat sensitive to your estimate of the relative height of the table to the arm. If you get that wrong by more than a few millimeters, it kind of jams or misses the ball when rolling. So it can be somewhat sensitive there, but I think that's something we could do with online model. answer your question?
So I'm also curious about the sensitivity to small errors here. It's hard to tell, but is that a rigid ball? Or is it
Yes.
somewhat deformable? So it
Right.
seems like it would be helpful to be slightly deformable, maybe larger radius.
Yeah.
Do those make it easier? Or?
I think it would, yeah. I think it would. Yeah, I would have liked to have done this on multiple different balls of different shape, but we have not tried that yet. I think softer balls would definitely be easier.
So Michael, why is it harder? I mean, it seems like you should just plug in the same equations with a different radius. Why would it be?
The vision aspect of this was the thing that took the most time. So right now it's using a pretty crude ball tracker. You know, this is one of the things where I think we should do more. We need to do more experiments.
Just curious on that note, is the camera, where is the camera? Is there more than one?
There's a few cameras, they're not being used other than to trap the ball.
Right.
Yeah, so you can see some of them positioned around the sides, and I guess you can sort of tell what this.
Okay, so you deal with the occlusion.
Yeah, exactly. There's enough cameras to deal with occlusions.
You guys consider, I feel like, I believe you can model this as a mixed complementary problem, right? Like you can, if you end up solving just the KKT conditions of the NEC problem, and the optimization problem.
The KKT, because we have quadratic constraints, so the KKT conditions are going to end up cubic.
Right, but I guess, I think there are existing solvers for these like mixed complementary problems.
So this is not a mixed complementary problem because it has an objective function, right? So,
well, I say once you put it in like KKT, like in the dual form essentially, right? You can pose it as like a bunch of these equations or complementary conditions that must be satisfied. So I believe you can probably solve it into that form. And I was just wondering if you guys looked into the type of existing solvers that might be able to work with this.
I'm not sure I'm totally following. I mean, I think if you look at the KKT conditions here, they will be cubic. They won't be themselves a mixed complementarity problem in the classical sense. If you start with the QP, you can look at KKT, and those are a complementary problem. But we have a QP with complementary constraints, so it's harder than that.
Right. Well, okay, yeah.
I mean, this is a special case of an MIQP. It's a special case of a QCQP. And not even that special. I think there's some statements about converting one to the other.
Right. Well, I guess I think I've seen one approach where essentially the actual kind of the I guess like the non-bounds side of the mixed complementary problem can be any nonlinear system. So it's not.
Oh, sure. So not a mixed linear complementary problem.
No, yes, no,
yeah, mixed
nonlinear.
nonlinear. Yes, I mean almost any. That's such a general class of problem. Like anything can be written that way.
Right. But I guess there have been existing solvers that seem to work really well.
You mean like very old like PathVI or something like that?
Yeah, I think Path is one.
PathVI is not getting anywhere near fast enough. Yeah, that I having tried that. Maybe there are, and I honestly haven't seen a lot of work on like PathVI in the last 5 or 10 years.
Yeah.
So I'm not sure if that's still being improved. I was very excited when that came out, but we didn't have it all. I think the other problem is like you're sort of going for global solutions at some level with those items. We're not. I think any sort of the hardest results. I don't know how much you want to lean on them, but I would be skeptical of global optimality. Good question. Thanks. Okay. All right. So done with the control part of the talk. Right. I think if we have relatively simple models now, 2, 3, 4, 5 contacts. I think we can do real-time MPC now for the first time, right? With some local strategy. But where do these models come from, right? And that's sort of been a big area, a growing area of research in the lab. And so this is sort of the problem setup I want you to have in mind. You're given data that looks something like this. Okay, this is traced in SE3 over time, and you want to learn a model for this system. Okay, so what's happening here? I mean, any prediction, any guesses? What's going on? Okay, something's bouncing. You think it's a ball? Okay. It rotates a little bit, maybe it's a ball, maybe not. We can't quite tell what it is, but it's bouncing, okay? How many times does it bounce?
4 times. 2 big bounces.
Okay, definitely 2. After that, we're not so sure, right? It becomes a little fuzzy. I think that's real. I mean, there's sometimes these events are obvious and sometimes they're not. Okay, what happens at the end?
It's to a stop.
Okay, it's probably not rolling because the coordinate axis is not changing. It's sliding, yeah, it's sliding. Sliding and sliding. We all have pretty good intuition for this, right? Right, we can sort of figure out what's going on. We can't quite tell what it is. And if I give you this, okay, we'd all know this is a ball bounce, right? We have intuition here. The problem now is I want to learn this function. So I want to learn a state-to-state transition function given x and x prime, and state. I want to learn this function times my theta. And this is not a nice function. This is a nasty function. It has this big step effect where this impact event occurs. Stuff that's going to hit in red, stuff that's not going to hit in blue. Very, very steep, potentially discontinuous, depending on how you want to model it or how you're handling the time sensitivity. And deep networks are, for the most part, inherently biased towards simplicity, biased towards low Lipschitz constants, biased towards smoothness via their parameterizations and memorization. And so these functions are actually really hard to learn with an unstructured deep network. And so take that real data actually came from the cube, and take 100 tosses of data and give it to a deep network. I should say a lot of this work was done by Sam Frommer, who's now a PhD student here at Berkeley, but not doing robotics anymore. And okay, so collected, I think the right side is collected in his room during COVID. Okay, so you throw a deep network at this problem, and you can try as hard as you can to optimize network structure and so on and hyperparameters. And you get something that looks like this, which kind of captures the bulk motion pretty well, but is really poor in orientation, doesn't understand anything about penetration. Doesn't work all that well. We think it should work better. And I'm going to sort of roll out the details for this kind of slowly, but to give a high level idea, what are we going to do? We're going to do two things here. So one is we're going to learn some parameterization that looks a lot like you might see in a physics engine. So if I think about how your simulator works, it has sort of two blocks shown in blue, which maybe compute things like sign distance and Jacobians, the collision detection, and so on. And then it has something that maybe computes the smooth forces, the mass matrix, those, and so on. And it takes those two things, which are nice differentiable functions, typically, and it stuffs them into the contact force solver. This is the magic red box. For instance, that solves your complementarity problem or solves your Majoko magic QP, whatever it may be. That's sort of the magic of your simulator, and spits out state transition forces and so on. Okay, so we're going to do two things. One is we're going to learn the nicely parameterized smooth things that would go into that contact force solver. Okay, and if we want to simulate, we'll take your favorite contact force solver and simulate with that. So simulation sort of looks the same. And then we're going to do one other thing here, which is we're going to play with the loss function. Okay? We're not going to simulate for our loss function. We're going to have some kind of implicit loss function that's going to better regularize our learning problem. I'll go into details on that down the line. So this is the rough framework, which we're going to do two things. We're going to change the parameterization, or we're going to change the loss.
Quick question.
Yeah.
I mean, maybe I'm jumping the gun. Like, so for the with the red box,
Yeah.
And if you're going to be, differentiating or trying to be smarter with those blue boxes, did you have to take into account some notion of efficiency so that you're not taking too much time away from the solver?
In what sense?
Just in the sense of like when you're actually computing the prediction of these dynamics.
No,
I guess how computationally heavy is the red box?
in simulation, that is most of your time. It
Right.
depends a little bit on how complicated your scene is. So if your scene has lots and lots of objects that are not touching but maybe touching, you might get stuck in doing collision detection. And this isn't a real simulation.
Right.
But in general, the red box is where most of the complexity would lie. And again, that's what differentiates one simulator from the next.
Mhm.
But the big thing I would say, without getting ahead of myself too much, is we're never going to run this red box when training, when learning. Okay, if I want to do rollouts later, if I want to use my model for something, yes, I'm stuck with that, right? But in learning, we're actually never going to run that. I'll show the kind of high level results here. Short answer, right, is we just get dramatic improvements in data efficiency over unstructured networks here. So there are lots of different ways we can parameterize our learned geometry. The blue line here is parameterizing as a polytope. The purple is as a deep network. We've improved on the deep network bit since the paper was not quite published yet. But in any event, we learned something that understands something about friction, understands about smoothness, and understands something about impacts. it doesn't necessarily always get the number of bounces or rolls right. I mean, essentially, we're trying to predict the toss of dice here, so this is a very chaotic system. But it matches, in particular, I would say focus on the rotational bit here. It matches the rotational bit much better. And with this fuse like 5 to 10 tosses, right, we can get a really accurate model. We actually ran this at ICRO as a demo live, where the robot would toss it 10, 20 times and learn a model. Okay, so I'll come back to details of how this works later. But first, I want to sort of give a little bit more intuition and argue a little bit more vehemently for why we think the structure is necessary. So after this, we sort of set about saying, okay, what can we really say about why standard approaches don't work? We've seen empirically they don't work. Can we say anything a little more? So first, we ran an empirical study. And here we said, well, we have this hypothesis that stiffness is really sort of one of the key properties that's driving this. And so let's go and examine, here we go in Majoko, which is varying stiffness, and see how that affects learning. So we'll have 3 different models: the soft, the stiff, soft, medium, and firm. This is the medium one shown here, which is kind of realistic-ish, right? But not, still you can see kind of sinks in as it rolls. And we'll look at our loss. And we'll break our loss into 3 terms. One is just going to look at how well does an oracle do. We add some noise to the data. And it turns out, okay, an oracle struggles a little bit in the stiff domain, right? This is simply saying the underlying dynamics themselves are chaotic. And therefore, an oracle with some noisy inputs to it is going to have greater error. We can't really do anything about this. This is sort of stuck on this.
I just want to clarify, which one was the worst one?
An oracle is the true model rolled out from a noisy initial condition.
So what is this screen model that you're using?
This is all in STEM, so we know the true model.
Okay.
Yeah. This is entirely a simulated result.
Okay.
And in sim, so we can do things like know the true model and play with the stiffness, right? Otherwise, there'd be a lot of confounding variables. So we can't do anything about this, right? I think some of the reviewers originally were asking whether this was the core problem, and we could say no, it's a problem, but it's not the key. Yeah.
So I just want to understand, are you saying this is aleatory uncertainty that's somehow built in, but isn't the simulator deterministic?
We have a noisy initial condition, so we've artificially affected some noise.
Okay, so with that amount of noise, then you get this kind of lack of repeatability.
Right.
Okay.
Yeah. Then we can look at our ability just to learn on the training data. So looking at the training loss now as compared to the oracle loss. And we really struggled, despite attempting many, many times to optimize hyperparameters and running things over and over again in the cloud, to simply just memorize data sets here. And you can see that in the blue line there for the stiff version, which is that the training loss really doesn't even go down as the amount of data increases. It stays stubbornly high, and significantly higher than the software version. So this is just saying, how well can you learn the training data? And the answer is not that well. Okay, and what this is coming down to is the fact that the loss landscape here is nasty, and the learner is not effectively optimizing over that. Right? Maybe you can do better than this, right? But I would say it's very difficult. And then the last thing we looked at was just our generalization error, and again, staying persistently high over the stiff data set and dropping nicely for the software versions. So, I think my conclusions from this empirical study were that, for one, if you're doing training and simulation, and your learning works really well when you make the sim soft, you should sort of question that, whether that's actually going to work on the real data or in a stiffer, stiff environment. You may have made your problem too easy, artificially easy, by simply softening the simulation. Things work in soft sims that maybe don't work for a harder domain. But this is okay. This is a pure empirical study. What else can we say about this? We also looked at some nice, trying to find some theoretical bounds here. And then there's some limited results that, in learning theory here that we can lean on, just to show, one example here. You could go out and show that your generalization error, okay, so how well do you do on NC data, can be bounded by the amount of data you have, but also by this Lipschitz constant. In fact, particularly the Lipschitz constant for loss with respect to your parameterization. So how stiff or how high Lipschitz is the optimization problem that you're trying to solve. And so let's look again at our toy problem here of this ball drop. So we're going to make this toy problem as easy as possible. We're going to say just learn the height of the ground, the single parameter. And what does our model look like here? Well, a model has this multimodality where we have contact, no contact here in this max function to try to write things simply. And the contact version has this 1 over dt. Okay, this is the discretization of the impact event. It basically says things are going to come to pass very, very quickly as it hits the ground. Okay, and so the Lipschitz constant here is 1/dt. It's very large. Okay, this is a discrete time approximation of the impulse there. So what this sort of comes down to is this is for the simplest parameterization possible. This is going to hold for any parameterization. If my loss looks like this 2-norm of prediction error, well, f theta is stiff. My loss is going to be stiff. It's inevitable, right? No trick with parameterization or no diff-sim approach is going to solve this problem. This is sort of fundamental to the loss choice. So we have to fix this issue with loss, right? And let's sort of take a step back and think about where these losses come from. What is the loss trying to do? It's trying to basically say, okay, I have some learned model and I have a data point. I just want to score how well that data point matches the learned model. Right? That's the fundamental goal here. And if we said both x and x prime are noisy, then it turns out the max likelihood choice here is to look at something like total least squares or errors of variables and look at graphics. Okay, so under this assumption that both x and x prime are noisy, we get a graph distance as our loss, which looks like this embedded optimization problem. It says find the point x prime in the x direction that minimizes graph distance. This would be a nice loss to pick. Again, it has nice interpretations like max likelihood. Okay. The problem with this, though, right, is that this is not tractable. Right, this optimization over f theta. Well, f theta is the thing I'm trying to learn. Am I really going to solve this problem, this nonlinear optimization problem, just to compute my loss? The answer is typically no. So what do we do in practice? We say, well, prediction error is pretty good instead. So just fix x hat to the data point x, and now our loss doesn't have an embedded optimization problem. It just looks like the book. And this is prediction error. This is what most people do. Makes a lot of sense. In fact, it's equivalent to graph distance up to the Lipschitz constant. Here, Lipschitz with respect to x. So a nice smooth function, low Lipschitz. This works quite well. Instead, I might as well just use prediction error. No need to try to do graph distance. Okay. But then, okay, what if my function looks more like this green line, and then my data point is over now shown on the right? Well, now there's a huge gap between graph distance, which is the thing I might care about, might think is the right choice, and the prediction error now. So these things stop being equivalent when that Lipschitz constant gets high. Again, going back to stiffness as this driver of complexity. When it's high Lipschitz, this is no longer. All right, so what are we going to do instead? Well, we can't compute graph distance. I'm not going to magically make that problem tractable. We'll try to do something instead. So instead, we're going to write down this implicit formulation of physics. That's going to say, this is for our clay ball drop problem. Still, my model says, well, my next velocity is a function of whatever my gravity forces are plus some force, and the force has to satisfy this complementary constraint. And now my learned parameter theta is now embedded in that constraint. So I could do the same thing before prediction loss, just writing it this way, where now it's an optimization over lambda such that this complementarity constraint holds. I haven't changed anything. This is the same prediction loss we saw before. It has the same problems we saw before. I could do something like diff-sim or soft simulation and say, well, just relax that complementary constraint a little bit. So rather than equal to 0, equal to epsilon, make epsilon some scalar variable. And this will work as well. I can now still kind of solve this inner optimization problem over lambda with my soft sim. I can differentiate it and so on. But of course, I've sort of changed the underlying model a little bit to introduce gradients. And the more I change my model, basically the bigger I make epsilon, the easier this problem becomes to solve. But of course, the worse my model gets. So we're going to do something slightly different here. And I think it's very slightly different, but I think different in a somewhat profound way. We're going to do a penalty method. At the end of the day, we're going to take that complementarity violation and we're going to stick it up in the loss function itself with some weighting parameter. So what is this doing? It's hypothesizing forces lambda which match the motion that we've observed. That's the first term there, and match the model that we're trying to learn at the same time. And with a good model and a relatively noiseless data, both of these terms will go to 0. And I think this is why it works here, is that both of these terms will go to zero. I'm not ultimately having to weight one error against one another. I'm simply reshaping the loss landscape. The true solution, at least in the noises case, actually doesn't change. I haven't softened my dynamics. I've softened my loss function. The true solution doesn't change because it achieves zero loss. But the loss function is dramatically reshaped. I'll show an example in a second. In the case of this ball drop, it turns out that the Lipschitz constant actually stops depending on dt. We had this 1 over dt scaling before. It actually goes away even as the limit as dt goes to 0. Depends just on alpha. And the alpha we pick is something on the order of 1 to like 10 to the minus 3 in that range. It's not a terribly big or small number. It turns out it doesn't really matter all that much how we pick it. Well, results are relatively robust. So another way to think about this, okay, is that it turns out simulation is really difficult for contact, but this learning problem is not as hard as simulation. We've observed the next state. We have X prime, measurement of a noisy potential measurement. We have a measurement. And we can use that measurement to essentially regularize the process of simulation, to smooth out the simulation process. So supervised learning is actually easier than simulation. So for our ball drop example here, if we ran with the original SIP dynamics and we get prediction loss, we get something that looks like that dashed line with the pink shading there, where if the ground prediction is too low, we actually have zero gradient. Why is that? Because, well, our data looks like the ball hitting the table, but our predicted table is too low, so our prediction actually never sees an impact, never predicts an impact. It just says, oh, your data looks like this, oh, they never hit the ground, no impact. So the gradient with respect to moving the ground up and down is 0. It's still not going to cause an impact. And then the other side, okay, parameters that are positive, you're predicting that the table is too high, and so you actually have data that punch through the surface. And so what does the simulator want to do? It wants to eject it as fast as possible. And so you get this really stiff response for that one-sided prediction error. So this loss landscape is horrible, even for this toy problem. With the implicit loss, though, it looks like that solid line, not convex. Okay, convex would be maybe a little too much task for, but a nice landscape to optimize over. Again, we haven't touched the global minimum, it's still there at 0, but we've reshaped the loss landscape. I'll give sort of one other interpretation here of what we're doing. So, there's two things. One is we've changed the representation, changed the thing we're learning. So we're learning an implicit representation. Right? If you think about this in a learning framework, we have some embedded optimization problem. That's the thing producing lambda inside our architecture, like a lot of these new implicit learning setups. And the standard approach here, the diff-sim approach, would be just to compute the output of this and compare. We are leveraging the fact that we've measured X. I think that's sort of the really important thing here. It's like, why take your inputs, pass it through, and get your outputs when you know the predicted output, right? You can use that inside the loss calculation. You can use that to change the landscape. And so, first off, we never simulate during loss evaluation. For forward predictions, of course, we simulate. Okay. We leverage this measurement of X prime. And it turns out we're still, I'd say, in the process of formalizing these statements. I think in some settings, we can say this. In the frictionless setting, we can say this. Friction's been a little bit nasty to do, but in some settings, we can actually relate this to graph physics. We can say that this implicit loss actually provides a nice bound for graph, independent of the original Lipschitz constant. Okay. We've applied this in a number of settings. So I showed the content nets cube data earlier. We've also done this for just sort of generic piecewise affine systems. So just kind of showing what that learning process looks like. Given some noisy measurements from XX prime transitions, it simultaneously learns the mode assignments and the dynamics in those modes. Okay, and you can sort of see the learning process on the right here. The modes are the colors, and it's sort of warping its prediction over time as it identifies the modes. This compares to more classical approaches who might use clustering first, try to identify modes, and then fit via linear regression. And this scales just way better. It scales to thousands of modes. It scales to very, very stiff systems. Works very, very reliably across a lot of patterns. Earlier work, kind of looked at learning geometry as either a polytope or as a deep sign distance function. Turns out the sign distance functions were pretty poorly behaved in this learning process. And what we've gone to recently, this is the work that we showed at ICRA, is to use a support function here, parameterizing the homogeneous input convex neural network. running over a relatively few number of trials. So it's a nice thing that we can say embed in a simulation, turn it to a mesh and so on if you want. So I think, even we have sort of a whole software framework that which spits out a mesh. So I'm going to move on to the last bit of talk, but just kind of summarize this, because I think this is sort of the key things from today. Is one is, black box approaches really struggle, okay? And I would say even calling them sort of black boxes is a little bit misleading, because standard approaches have biases. They're just not the right biases. Okay, there's some bias that you've encoded in a transformer or in the CNN. It's just not an appropriate bias for these stiff, non-stiff problems. And so there's two things I think are important. One is the representation helps. Okay, representation is the same thing that we use in DivSim, but I think it's also not enough. I think the more important bit here is how the implicit loss changes the landscape, and it enables better generalization and enables more effective training. Any questions before I switch topics? How long do I have?
A little after 5. I mean, we sort of wrap up around 5.
Okay.
You can go a little later.
Okay. I'll be relatively quick here for the last bit. So one thing I'm throwing out as well is that we've been this tendency sort of people taking these data sets and playing with them. So this is some nice work from DeepMind recently from Kelsey Allen and others. They showed that they actually could take our data set, both our sim data sets and our real data sets, and do pretty well with graphical networks. Actually got better performance than we did, with one caveat. And the caveat is they actually use ground truth time distance as a feature vector in their training. So what I would take away from this is more clever learning can definitely help you, right? So I think the graph structure is really natural, and I think that they made some really intelligent choices in going to that. The other thing I would say is that because they feed it this time distance, they don't have to do this mode identification problem simultaneous to the dynamics learning problem. And I think that's sort of the really hard aspect potentially here, is that if you know the mode ahead of time, okay, you have template sensors, or you have some other independent way of identifying what's touching what and when, then you can do really well with more or less kind of standard approaches to deep learning. It's doing these two things together that's actually really hard. All right, so lastly, I want to wrap up and just talk about a little bit about simple models here. So, if I think about how I go from rolling the ball on the table to really what I want to do, which is entering a cluttered room and dealing with a bunch of stuff, is a key part here is I have to look at this nasty cluttered environment and say, most of this is irrelevant. Okay? There's thousands or millions of context modes. Even for something like playing with my phone, there's thousands of possible context modes. This is not a useful way to think about the problem. I need a way of distilling down the multimodality of this problem to something more tractable. And I need some way to uncover a single model that's going to be appropriate for a task. So we'll take as an example here this three-finger manipulation problem. This is the ODRI tri-finger here in Sim. It has thousands of modes, again, and sort of, approaches which kind of just tackle this problem as it is, whether model-based or RL, are going to either be intractable or require too much data. And so, the key insight here, I think, is relatively simple, is we don't need this many modes, right? They're not necessary. We can still be successful while reasoning over a fewer number or a smaller problem. But what is that smaller problem and how much complexity is really required? So we'll formulate this problem like this. Suppose we have the true problem, potentially unknown true dynamics, some nonlinear complementarity thing, for example. We don't even assume we have access to this, we just assume it exists somewhere. But we want to approximate that with this linear complementarity version. We want to say, let's do the linear because that's going to enable real-time control. We can do MVC over there. We're going to try to find something with a few number of modes. So we'll say the lowercase lambda is much smaller dimension than the true number of complex. And we like to say something like, well, if we use the blue thing for control, we get approximately optimal performance. Okay. We minimize the performance loss. And the approach that came up here is really simple, not even novel, right? It's to say, well, run our model learning in a loop with the MPC. Okay, so it collects some data, the original at the beginning, some random data, but then eventually on policy data. Use that data to run a model, use that model to do control, and train. Turns out this is shockingly effective. Okay, and so on synthetic data here, a slice of some high-dimensional system, we can cut down the number of modes by an order of magnitude or more with really minimal penalty in terms of cost. So the true modes here shown on the left, colorized, the learning process on the right. And I think the key thing here is that, yes, the true system has lots of modes, but if you want to act optimally, well, you don't need that many modes. And under this assumption of taking optimal actions, it turns out the optimal policies for the learned approximate system are relatively similar, and the closed loop behavior is relatively similar. We do this on manipulation as well. So this is the tri-figure problem, training over 4 minutes of data here in real-time data, or wall clock data in sim, and achieving really good performance. This is not the hardest task. I'll be first to admit that. Right? It's a position and orientation task over a modest domain of possible target locations, but it's doing so from scratch, and no prior information about that cube in 4 minutes. Surprisingly robust to perturbation. We're not training it with any kind of domain randomization, which just happens to be robust due to the simplicity of the control policy, I would say. And in this case, learning a model with 32 modes. The modes here are totally artificial. Maybe I'll skip this, but they sort of loosely correlate with context configurations you might see. This is all purely an empirical observation. Another thing to point out here is even with this simple linear complementary model, we find that the policy makes and breaks contact on different bases of the cube, depending on what the target is. It's not always dragging the finger to the nearest space. So, just to wrap up, I think we've, tried to tackle bits and pieces of this. There's still kind of a long way to go. I didn't get a chance to talk about any of the walking or running work we do in the lab. We also have a CASI, we do some legged locomotion, some running, some jumping. The jumping video on the top right is brand new from this weekend. First time it successfully made the jump. With similar kind of ideas in mind about how to design control policies that can meet cinematic fact events and deal with simple models as well. I think we're still scratching the surface. I think there's there's obviously a very big gap between the results I've shown today and what we really want to do in unstructured settings. I would sort of argue philosophically a couple of things, right? One is I don't think we're going to solve robotics via data. I think it's going to take some domain expertise in combination with that data. And I'd also say, to echo something I said earlier, I don't think there's anything quote unquote standard about standard approaches. I think methods that people are using right now have biases built in. There just might not be the right biases. So it's important to think about how the structure of your problem can better fit within the type of algorithm you're using. And with that, I will conclude. I'm going to thank the students who did all this work. So before saying anything, Al Identical in particular did a lot of the control work, currently looking for a postdoc. He's looking for a postdoc. He's fantastic. Matt Helm and David Bentini did a lot of the learning work. And Wenshi Jin did the simple model learning stuff at the end. Thanks sponsors as well, and happy to take any questions.
Michael, so great talk, and I really like the way you're thinking about these problems. When you just want to, when you look at the three-fingered hand example, right? And you said, it responds to disturbances. So I'm curious, what would be involved in taking it to the next level to put it in real?
We have to build the real one first.
You what?
We have to build it first.
I thought it was existing already, that there was a test bed or something.
There's this for the three-fingered hand. There's designs online, and we just have been trying to assemble it. So that's.
I see. Okay, because I thought I remember there was some kind of competition where they were going to run the different control models, and then you could just.
That's true. There was, yeah.
That was passed. Okay.
Yeah.
Okay. So you are building it.
Yeah.
Okay.
I think it's been like 90% built.
Oh, okay. Okay.
It's a matter of finding.
Oh, yeah.
But I think, I don't know, if anyone who's done real robots knows, right? Going from sim to real is not a trivial task. I expect we'll have to do some problems.
But do you think they'll be in the sensing aspect, the perception? Or?
So I didn't talk about sensing and perception today. That is very much on the horizon for what we need to do. I think, we need to get rid of the motion capture bits, the April tags. We need to put in real sensors. I think we need to use tactile sensors as well. I think there's a really nice coupling between how we think about motion and vision and tactile sensing. They're all sort of coupled by geometry to some extent. And if you think about what we're learning geometry. Okay, vision is pretty good at producing crude geometry estimates. tactile sensing is obviously very connected to geometry as well. So I think there's a room for these things to benefit one another, right? To learn something about an object that's included because it's touching something by how it interacts with that other object. That's on like the 2-3 year time.
Michael, can you hear me? This is Claire.
In your manipulation example towards the end, did you find that you're learning something about the optimal way to manipulate the objects, something about the manipulation itself rather than how to optimize the system for manipulating it? So if you're trying to translate it and rotate it, are there certain principles that you're finding that also generalize to other systems?
Yeah,
So
that's a good question. I don't know. You know, the model we're learning here is very much, it's a relatively low dimensional black box, but it's still a black box. It's linear complementary model. So we've tried to interrogate it, we've tried to understand what the modes mean. But it's a pretty imperfect understanding. So I don't know.
A lot of the problems that you're trying to solve seem to come from the rigid body interaction. Of course, there's a move towards, you know, softer skins at the very least, which is going to change the mechanics of that interaction. Does it also make the computational problem easier if you were to actually have a softer ball at the end of your
It
rope?
kind of depends, right? I think there's a gradient where you say the interaction becomes soft, but I can still get away with a finite dimensional representation of the state. And that might make your problem easier. You still have pretty max, you know, the friction tends to get greater as you go to softer materials. So the frictional stick sub effects can become harder, but maybe the normal force aspect becomes easier. Turns out actually friction tends to be the harder of the two from a computational perspective. So it's not obvious that it will get easier, it might. But then if you get to like fully soft things that deform and change shape, then you have to deal with that in the dimensional state or some approximation of it.
I mean, obviously, I showed you our sort of split sensor earlier. If you had a direct observation of motion or slip or the onset, how would that fit into this?
I think that so I'll lump tactile sensing with that as well. I think that it helps a lot, right? So we have this inference over possible contact forces. If you're measuring the contact force or you have some direct observation, I think that can use that directly to either bias that inference problem or replace it altogether. Now, you know, you get to a more complicated scene, you're only going to have partial observations here, right? You're going to touch one object and that object touches something else. So you're never going to sort of have a fully sensorized environment where you know all the forces, but knowing some of them, I think, could be really beneficial. Something we thought about at the time.
Well, I would be interested in your perspective on practical sensors. So I think one of the reasons why they're not adopted is because they need to be recalibrated often, they break, they change, but that doesn't make them useless. They just might actually change their readings. You know, if we don't treat it as a perfect observation, but as you know, it kind of fits into the theme of your approach to say, well, how do we handle this with an imperfect system?
Yeah, that's a good question. You could certainly, you know, if you had a noise model of a sensor, you could use that and use it as a bias. If you didn't have any noise model, you sort of knew that your sensor was spitting out, you know, some loosely correlated version of force. Suppose you could try to calibrate it simultaneously to the model learning. I'm thinking on my feet now, so what I would try first, and probably the first thing. I don't know how well that would work. Not a lot of data though, but potentially could, right? I mean, you know, as far as using observed motion to calibrate for something, there's a challenge there in the sense that, like, you know, masses of objects without force measurements are typically unobservable. So like the mass of the cube, for instance, is unobservable. I think if you don't have any scale for your force sensor, you're still going to be in that scope where there's no global scale framework, but barring, you know, that aside, it's fun to do it.
there is a question in the chat. Let's see. Is your speaker on mute or?
Yes, it is.
It is. Okay.
Can you hear me?
Yes. Yeah.
Oh, okay, great. Yeah. Thank you, Michael. That was a great talk. This is Claire. I wanted to ask about the work that you presented earlier, the ADMM work. And I think it really might apply nicely to a lot of these kind of older collision avoidance problems that were done in air traffic control, for example, where people kind of maneuvered the problem around to make it fit into a kind of mixed integer linear program format. It seems that the complementarity methodology and implemented using ADMM that you presented is a very nice way to kind of rethink some of those optimizations, some of those non-convex optimization problems.
Yeah, it's a good point. Francisco was saying something somewhat similar earlier today. The short answer is I'm not totally sure if it is a good idea or not. I don't think I would recommend, say, ADMM as a generic substitute for solving the MIQP. I think there's something in this case about the complementarity constraints that makes branch and bound particularly ineffective. You know, for something like collision avoidance, yeah, ADMM, though, I find it sort of a hard algorithm to really kind of intuitively reason about. You know, I can say why I think it works well in this setting, and I'm not sure it applies to the collision avoidance problem you're talking about. But I think that the decoupling in time is really critical. And I think the sort of other aspect there is that by in these alternating stages, allowing yourself to hypothesize possible but non-physical contact forces, you allow this mode exploration to occur. And so, yeah, in the avoidance problem, I suppose like the force is taking the role of the dual variable for the collision avoidance constraints.
Yeah. Yeah, and I think one of the challenges is that there's always kind of these artificial methods for restricting the number of vehicles in the neighborhood because of the computational constraints with the MILPs or the mixed integer nonlinear programs, or basically those methods. And it seemed like this framework could perhaps give a new insight into that.
Yeah.
Anyway, something to look at and think about, I thought.
Yeah, I'd be happy to think about that or chat about that later.
Yeah, thanks. Nice talk.
Thank you.
Good. I think we have time for one more question and then we have to wrap up.
You would wait, yeah.
Thanks for the nice talk. You showed some cool manipulation work that independently showed the nice Cassie working videos. I was wondering, do you have a plan to incorporate a manipulator on top of Cassie maybe in the future, or make your own humanoid?
Oh, okay, so I have no real expertise in design, so my own humanoid, that's a concept that terrifies me. No, you know, to the first part, no, not really. You know, I think the kind of problems we're thinking about tend to skew more towards the fundamental side. And so, you know, from that perspective, I think sticking an arm on Cassie, while it can enable, you know, a broader scope of tasks, it's just going to make the integration effort harder than it already is. I think we probably won't do that. But maybe on a simpler mobile manipulation platform, that might be interesting.
I had a question about the stiffness comment. So in my head, it seems like stiffer interactions correspond to like higher frequency and time. Or for an example of a bouncing ball, if it's stiff, it's a V shape. If it's soft, it's more of a U shape. And there's some literature and graphics relating to NeRF, which shows that neural implicit functions can't represent low or very high frequency things, which is why positional encodings exist. So I wonder if you think grabbing positional encodings and putting your position into that before passing it into your neural network might help represent these higher frequency rigid interactions.
So I think, you know, I think, yes, definitely that helps on the representation side, right? In the same way that I think that parameterizing learning the parameters of the simulation help on the representation side. I think that's an important step. I don't think that solves the issue of the loss of scale. That if you're fundamentally doing prediction comparisons, right? Rolling out whatever you're learning, however it's parameterized, you're comparing that with data, I think you're going to be stuck with the stiffness in your loss. So it helps in the representation side, help a little bit for generalization, but it doesn't change the loss landscape. So learning and training is still good.
Thank you so much.